Sound is something we experience pretty much every second of our lives, right? But have you ever stopped to think about what it actually is? What is sound? I mean, really think about it. When a guitar string vibrates, or you just clap your hands, what's actually traveling through the air to your ear? What is that thing that your brain then calls sound? It feels like it should be a simple question, but the physics behind it? Oh, it's absolutely fascinating.
So, to really get a handle on this, we need to do something kind of weird. We've got to zoom way, way in on the air. Yeah, that seemingly empty space that's all around you right this second.
Because here's the thing, that air isn't empty at all, not even close. It's more like an invisible ocean. It's just bustling with atoms and molecules, all constantly moving, bouncing around and bumping into each other and into everything else in the room, including you. And all of that bumping, that relentless bombardment from every direction, it creates this constant force on every single surface. In the world of physics, we've got a name for that: static pressure. You probably know it as atmospheric pressure. It's just the normal baseline state of the air we're all sitting in. And believe me, this pressure is no joke. We're talking about 100,000 newtons per square meter at sea level. Now, what does that even mean? Well, to put that in perspective, it's kind of like having the weight of a small car spread out all over your body. Whoa, right? The only reason we don't get squished is because that pressure is pushing on us from every direction at once. It's all perfectly balanced out. Okay, so we've got our invisible, pressurized sea of molecules. Now comes the fun part. Let's see what happens when we make a ripple. Just picture a loudspeaker, the cone that moves back and forth. As that cone pushes forward, it literally shoves the air molecules that are right in front of it. It just squishes them together, forcing them into a smaller space. And this really simple back and forth motion creates two totally different effects. First, you get that area where the molecules are all squeezed together. That's a zone of high density, high pressure. We call that condensation. Then, when the speaker cone pulls back, it leaves behind this gap, an area of low density, low pressure, and that's called rarefaction. So as that speaker cone pushes out, it kicks off a chain reaction. That first little pocket of high pressure, that condensation, it starts to move away from the speaker because it's pushing on the next layer of air molecules. And right on its heels, as the cone pulls back, you get that little vacuum, that low pressure zone of rarefaction. So this pocket of stretched out molecules is chasing right behind the pocket of squished together ones. And really, that's the whole magic trick. That's the essence of what sound is. It's just this repeating, traveling pattern of high pressure and low pressure, a continuous wave of condensation and rarefaction moving through the air. All right, so we've got our pressure wave, but how does it get from point A to point B? How does it travel from that smicker all the way to your ear? Do the actual air molecules fly across the room? What do you think? Okay, here's a fantastic way to picture what's going on. Imagine a long line of golf balls, but they're all connected to each other with little springs. Now, if you push the first ball, what happens? It doesn't go flying across the room, right? Nope. It just compresses the spring in front of it and bumps into the next ball, which then bumps into the next, and so on and so on. The energy travels down the line, but each individual golf ball just kind of wiggles in its spot. This kind of wave has a specific name. It's called a longitudinal wave. That just means the little particles, our air molecules, are wobbling back and forth in the same direction that the wave of energy is traveling. And that, right there, is fundamentally how sound works. And the only reason this whole domino effect works is because air itself is elastic. It's got a springiness to it. I mean, if you've ever blocked the end of a bicycle pump and pushed, you know exactly what I'm talking about. Air pushes back. So when it gets compressed, it wants to expand. And when it gets stretched out, it wants to snap back. That springiness is what passes the energy along so well. Now, here's where it gets even cooler. This whole chain reaction, this domino effect, it doesn't happen at the same speed everywhere. Not at all. The material that the sound is traveling through, the medium, it matters a lot. So let's talk about air. In the atmosphere around us, sound zips along at about 330 meters per second. That's over 700 miles an hour, Mach 1, which sounds super fast, right? But when you compare it to the speed of light, sound is practically crawling. But what about in water? Well, that's a whole different story. Water is way stiffer than air, so sound travels more than 4 times faster. We're talking around 1,500 meters per second. Bam!
And then you get to something really solid and stiff, like steel. Get this. The speed of sound in steel is a blistering 5,200 meters per second. The molecules are packed so tightly together that they pass that vibration along with incredible efficiency.
So what's the big takeaway here? It's basically a battle between two things, stiffness and density. And while being more dense can slow a wave down a bit, stiffness is the real champion here. The stiffer the material, meaning the tighter the springs are between the molecules, the faster that wave's going to travel, much, much faster. And this difference in speed, especially how slow sound is in air, has effects you've probably noticed yourself. Think about being at a huge concert or a big sports game. If you're way in the back, you might see the drummer hit the cymbal and then hear the crash a split second later. It feels out of sync, right? That's because the light gets to your eyes almost instantly. But the sound wave, well, it has to take its sweet time traveling through the air to get to you.
All right, let's pull all of this together. Let's zoom back out and look at the big picture of what sound really is.
Okay, so if you remember just one thing from all this, let it be this. When you hear something, the air molecules from the speaker do not travel all the way across the room and into your ear. That's not what happens. What's really happening is that a wave of energy, a little disturbance of pressure, is passing through those molecules, and the molecules themselves end up pretty much right where they started. But this brings up a really interesting question, doesn't it? If all sound is just this pressure wave rippling through the air, then what makes the deep thumping boom of a bass drum different from the high, delicate chirp of a bird? What's different about their waves? How do those differences create the millions of sounds we hear every day? Well, that sounds like a perfect topic for our next explainer.